Finnish engineers just proved that a silo of ordinary sand, the kind sold at any hardware store for a few dollars a bag, can store enough heat to carry a home through a brutal Arctic winter with no combustion, no gas line, and no utility meter running, no exotic chemistry, no rare earth minerals, no complex electronics, just sand, a steel container, a resistance coil, and the same physics as govern thermal mass. Since the first human being stacked stones around a fire, the question is how a material that's simple can do something that's sophisticated, and whether an off-grid homesteader in Alaska can actually build one for $200. Because if the answer to both of those questions is yes, then one of the most pressing problems in cold climate off-grid living may already have a solution sitting in a bag at your local hardware store, waiting to be taken seriously. Let's find out. The idea of storing heat in dense material is not new. It is, in fact, one of the oldest engineering principles in human history. The Romans built hypocausts beneath the floors of their bathhouses, circulating hot air through raised stone platforms that absorb heat during firing and release it slowly for hours after the flames died down. In the American Southwest, adobe construction was not merely an aesthetic choice. The thick earthen walls of Pueblo architecture absorbed solar heat during the day and radiated it back into living spaces through the night, passively regulating interior temperatures in a climate defined by extreme daily swings. In Scandinavia, soapstone masonry stoves called tulikivi were designed on the same principle. A short, intense fire loaded the dense stone core with heat, which then bled out steadily over 12 to 24 hours, keeping a home warm long after the fuel was exhausted. The underlying physics in every one of these systems is identical. Dense, dry materials with high specific heat capacity absorb thermal energy and surrender it slowly. The denser and drier the material, the more energy it holds per unit of volume, and the longer it takes to release that energy to its surroundings. For thousands of years, builders and engineers understood this intuitively even before they could quantify it. The modern off-grid problem is that intuition was largely abandoned in favor of combustion. Propane tanks, heating oil drums, and cords of firewood became the default answer to cold climate energy storage. And for most of the 20th century, that answer was cheap enough that no one looked too hard for an alternative. But the economics of off-grid heating have shifted dramatically. Propane prices in remote Alaskan communities have more than doubled over the past decade, driven by supply chain costs, transportation logistics, and the compounding expense of reaching communities that road infrastructure simply does not serve. A single winter heating season for a modest off-grid Alaskan home can consume between 800 and 1,500 gallons of propane, at prices that in remote areas regularly exceed $5 per gallon. The math is unforgiving. The alternative that emerged from the solar revolution, lithium-ion battery storage, introduced its own set of problems for cold climate applications. Lithium-ion chemistry is acutely temperature sensitive. At minus 20 degrees Fahrenheit, a lithium battery bank can lose 30 to 40% of its rated capacity. At minus 40, some chemistries approach complete functional failure. This is not a marginal inconvenience. It means that the moment a cold climate off-grid system faces its highest heating demand, the energy storage technology most commonly used to meet that demand is operating at its lowest efficiency. The gap between what the system needs and what it can deliver is widest precisely when the consequences of that gap are most severe. There is, in other words, a specific and critical vulnerability at the center of most off-grid cold climate energy strategies. And it is a vulnerability that a small Finnish startup decided to address not with new chemistry or advanced electronics, but with one of the simplest and most abundant materials on the surface of the Earth. Polar Night Energy was founded in Finland, a country where the relationship between winter and energy is not abstract. Finnish winters are long, dark, and genuinely cold, and the national grid has historically been heavily dependent on imported energy during peak heating months. The company's founding engineers recognized that the core problem of renewable energy, its intermittency, and the core problem of cold climate heating, its relentless continuity, were mirror images of each other. Renewable sources like wind and solar produce energy in bursts that do not align with demand. Heating requires energy in a slow, sustained release that does not align with generation. The question was whether there was a storage medium that could bridge that mismatch cheaply, safely, and at scale. Their answer was dry silica sand. The physics of why sand works where water fails at this application is worth understanding clearly, because it is a foundation of everything that follows. Water is an excellent thermal storage medium at moderate temperatures. It has a high specific heat capacity, it is abundant, and it is non-toxic. But water boils at 100 degrees Celsius, and above that threshold, it transitions to steam, expanding in volume by a factor of roughly 1700 and generating significant pressure. Any water-based thermal storage system operating above boiling point requires pressurized containment, pressure relief valves, and engineering controls that add cost, complexity, and risk. This places a hard ceiling on how much energy a water-based system can hold per unit of volume. Dry silica sand has no such ceiling. It does not change state. It does not boil, pressurize, or expand. It does not corrode the container it sits in, and it does not react chemically with the resistance elements used to heat it. Sand can be heated to 200, 400, even 600 degrees Celsius, and it remains exactly what was at room temperature, a dense, stable, inert solid. That stability is what makes it so effective. 1 cubic meter of sand heated to temperatures in that range stores roughly 60 to 70 kilowatt hours of usable thermal energy. For context, the average American home consumes approximately 30 kilowatt hours of energy per day across all uses. A single cubic meter of properly heated sand holds more than 2 days of total household energy demand in a form that requires no electronics, no cooling system, and no maintenance to preserve. Polar Night Energy proved this principle at industrial scale through a series of landmark deployments that have attracted significant attention from the European energy sector. Their installation at Pornainen in southern Finland stores heat in thousands of tons of crushed stone, serving district heating infrastructure for the surrounding community. Their Voxy project extended that model further, demonstrating that the same system could be charged using surplus renewable electricity purchased at spot prices that, during periods of high wind or solar generation, approach zero. The financial logic is straightforward and powerful. When renewable energy floods a grid faster than conventional demand can absorb it, wholesale electricity prices collapse. A sand battery charges during those windows, converting near-free electricity into stored heat. That heat is then discharged during winter peak demand, when energy prices are highest and heating needs are most acute. The battery essentially arbitrages the difference between the cheapest moments to buy energy and the most expensive moments to need it. The industrial proof is compelling. But the question that matters for an off-grid homesteader in Alaska is not whether this works at the scale of a district heating network. It is whether the same physics can be compressed into a system that costs $200 to build and fits inside a utility room. The answer is yes, with the understanding that scale determines output, not function. The core of the residential DIY build is a standard 55-gallon steel drum, the kind used in industrial settings and widely available through farm supply stores, equipment dealers, and online marketplaces for between $30 and $50. Steel is the right container for this application because it tolerates the high temperatures the system operates at. It conducts heat efficiently to the sand core packed inside it, and it is mechanically robust enough to handle repeated thermal expansion and contraction cycles over years of use. At the center of the drum, suspended within the sand core, sits a resistance element. High-temperature industrial immersion heaters, or nichrome resistance wire coils, serve this function. These are the same basic components used in industrial kilns and high-temperature furnaces. They convert electrical energy into heat with an efficiency that approaches 100%, meaning virtually no energy is lost in the conversion process. The resistance element is connected directly to the electrical input, and this is a critical design advantage that separates the sand battery from lithium-ion storage. Lithium batteries require charge controllers, voltage regulators, and careful management of charge rates to prevent damage. A resistance coil accepts raw, unregulated electricity directly. Surging voltage from a wind turbine in a high gust, irregular output from a solar array passing through cloud cover, any electrical input, regardless of consistency, is simply converted to heat. There is no damage threshold to manage and no regulation equipment required. The drum is then packed densely with completely dry silica sand around and above the resistance element. Moisture is the enemy of the system, not because it damages the sand, but because water trapped in the core absorbs energy as it vaporizes rather than storing it as thermal mass, reducing efficiency. Sand purchased in sealed bags from a hardware or masonry supplier and kept dry before packing is sufficient. No special grade or treatment is required. Running through the sand core is a coiled length of copper pipe, arranged to maximize contact surface area with the heated mass. This is the heat exchanger. Air or water circulated through the copper coil picks up heat from the surrounding sand and carries it out of the drum to wherever it is needed in the home. Connected to a radiant floor loop, the exchanger warms the water circulating beneath floor panels throughout the living space. Connected to a simple air handler, it heats incoming air before it is distributed through ducting. The copper coil requires no pump to function passively if connected to a thermosiphon loop, though a small circulation pump improves distribution efficiency significantly. The final layer of the build is insulation. Mineral wool, also sold as rock wool or slag wool, is wrapped around the exterior of the drum in as thick a layer as the installation space permits. Mineral wool tolerates the high surface temperatures the drum reaches during charging. It does not compress over time in the way that fiberglass insulation does, and it dramatically slows the rate at which heat leaches from the drum to the surrounding air. A well-insulated drum can hold a significant portion of its stored thermal energy for 48 to 72 hours without any additional input. Total material cost of this complete build, drum, resistance elements, sand, copper pipe, and mineral wool, comes in consistently under $200 when sourced through standard retail channels. What this produces is a unit with no moving parts, no combustion, no carbon monoxide risk, no fuel delivery logistics, and no ongoing operating costs beyond the electricity used to charge it. In an off-grid Alaskan context, that electricity frequently costs nothing at all. The off-grid energy profile of an Alaskan homestead follows a pattern that is almost perfectly suited to thermal storage. Summer brings extended daylight, sometimes 18 to 20 hours of usable solar generation per day, producing far more electricity than a household can consume or that lithium banks can safely absorb. Autumn brings frequent storm systems and sustained high winds, generating strong turbine output during exactly the period when solar generation is beginning to decline. These are windows of energy abundance, and in most off-grid systems, that surplus energy is simply wasted because there is nowhere for it to go. The sand battery solves that waste problem at its root. During a high wind event, raw turbine output flows directly into resistance coils. During a long summer afternoon, excess solar production that would otherwise trigger charge controllers to disconnect the array is instead diverted into the thermal core. The drum absorbs that energy as heat, storing it in a form that does not degrade, does not require temperature management, and does not lose capacity because the ambient temperature outside has dropped to -30. When winter arrives and generation falls while demand rises, the stored heat bleeds out to the copper exchanger into the home's heating system. There are no switching systems, no complex controls, and no decisions to manage. The thermal gradient does the work. Heat moves from where it is concentrated to where it is not, and the insulation envelope simply determines how quickly that transfer happens. This is, in its deepest logic, the same principle that the Pueblo builders of the American Southwest understood when they stacked their adobe walls. Store heat when it is available. Release it when it is needed. The difference is that a sand battery stores electrical energy converted to heat rather than direct solar radiation, and it does so in a container that can be built in an afternoon from materials available at any farm supply store. The sand battery is not yet a whole home heating replacement at the scale of a single 55-gallon drum. One unit provides meaningful supplemental heat and substantially reduces combustion fuel consumption, but a complete heating system for a cold climate home requires either a significantly larger vessel or multiple units linked through a shared heat exchanger loop. A 275-gallon intermediate bulk container, the plastic and steel cage totes commonly used for liquid transport and available secondhand for under $100, lined internally with a steel sleeve and packed with sand, multiplies thermal capacity by a factor of 5 at a material cost increase of less than 50%. 3 drum units connected in series to a single radiant floor loop can supply the baseline heating needs of a well-insulated 800-square-foot cabin through a sustained cold snap with no additional fuel input. Polar night energy's industrial trajectory points toward where this technology is heading at the residential level. As their grid-scale deployments accumulate operating hours and demonstrate long-term durability across multiple Finnish winters, the case for purpose-built residential thermal storage units becomes easier to make to both investors and regulators. Pre-engineered residential sand battery kits, factory insulated and sized for direct installation, are a logical next product category. Several European manufacturers are already developing in that direction. But the deeper significance of the sand battery is not the product roadmap. It is what it represents as a category of solution. In a decade defined by the search for better battery chemistry, rare earth extraction, and increasingly complex energy storage technology, the sand battery works because it refuses to be complicated. It stores energy as heat in a material that costs almost nothing, requires no mining of critical minerals, contains no toxic compounds, presents no fire or explosion risk, and will function identically in 50 years as it does today. The physics do not depreciate. For the off-grid homesteader in Alaska staring down another winter with a propane gauge and a tightening budget, that simplicity is not a limitation. It is precisely the point. The most resilient energy storage systems are the ones that have the fewest ways to fail, and a drum of sand with a heating coil inside it has almost none. No battery management system to malfunction, no electrolyte to degrade, no delivery truck that may or may not reach a remote driveway in February. Just sand, just heat, and the same physics that kept Roman floors warm 2,000 years ago, now charged by the wind coming off the Alaska range and stored until the coldest night of the year demands it back. The solution was never exotic. It was just waiting to be taken seriously.